All right, cool. Okay, hope you guys can see that. Everything good? Sound okay? Yeah, Joe's awake.
Good.
There was some concern as to whether Joe was going to be awake, but he made it. All right, you guys, great. So we're going to talk today about our next category of disasters, flooding. Again, always with the recollection that we're talking about these stressors in isolation so we can describe them, but really these things oftentimes are feeding back on one another. A hurricane might induce flooding, which might cause a fire and all this and that, all that good stuff. Okay, so let's talk about flooding. Flooding is going to be the most, from year to year to year, flooding is the most costly weather-related disaster we have. It just is, it's sort of here all the time and it's constantly causing problems. And as you guys know, I even had some internal house flooding the other week. So I'm hypersensitive to it this particular go around. To start off with, let's just get a little bit of bigger picture here in terms of weather context, and that is obviously, as with so many resources on our planet, things are not homogeneously spread out. And that's clearly the case in terms of rainfall patterns. And so this is an average of about 30 years worth of recent data. And this is showing us which, when is it most wet in these different regions around North America. And so for us, clearly, January, February is where we in California really get the bulk of our, or at least that is the wettest month on average. Things can shift here and there, but pretty much, and you might have seen, someone might have posted it in our Scoop It, but we also have some readings that touch on this, that basically we've lost now essentially a month or so in terms of our rainfall patterns here in California. So it's a new study that just came out. And so basically, again, the rule of thumb historically was October 15th is when we would expect the rainy season to start in California, particularly Southern California, but California as a whole was October 15th was a general rule, with the idea that we would, historically, little bit of pitter patter, kind of sort of fog, light, misty kind of rain in October. By the time we get to November, Thanksgiving time, we're maybe getting a few lightish showers kind of thing. And then really getting into the first significant, or what we might call the first major rain of the season, usually defined as something like a rainstorm that produces more than 1/2 of an inch to an inch of rain in one system, one event. That usually is going to hit around Christmas to New Year's, that time frame. That pattern still seems to be holding up, but we're losing the tails, we're losing the edges. And so now the rainy season is more starting in November typically instead of October. Regardless, the wettest month is remaining that late December, early January sort of time window there. Okay. Another key thing that we oftentimes think about when we think about flooding and downpours and all that good stuff is ENSO, or El Nino Southern Oscillation. So does anybody remember what El Nino is from your other classes, or anybody remember where it comes from, or why we refer to it by this term?
Isn't it I might be totally wrong remembering this, but
I think Sabrina's talking, but I can't hear you.
Oh, really? Can you hear me now?
No.
I can hear her.
I wish I knew ASL, then we could just do it that way.
I can hear her too.
Somebody else, Gabby or Joe or anybody else, go ahead, chime in.
I was just saying I can hear Sabrina.
Man, I can't hear. Maybe it's me. Maybe you guys are talking, but oh man. Okay, hold on a sec. What's going on with my massive technology? Try again. You guys try talking again. See if it works now.
Hey.
Okay, perfect. Sorry. I did not mean to say that Sabrina or Gabby was lame. It was clearly me. Go ahead, you guys take a stab at it.
Sabrina,
it-
you go.
Isn't it a pressure system that starts in South America and heads west?
Kind of, yeah. So we'll talk about that. Yeah, that's definitely part of the story. But do you guys remember why we call it El Nino as opposed to some other random name or some other mathematical term or something?
Something with fish, anchovies, the
Yep.
boy.
Yep.
Oh,
Isn't there a story of a fisherman with when the warm water comes up in
Yep.
the west, whatever?
Yeah, so you guys are right. So we're the story is from South America. So if we go down to Chile, Argentina, that part of South America, the Pacific coast, basically the Peruvian anchoveta, this sardine-like fish, super important for the economy, super important for livelihoods, etc. And folks started noticing that sometimes those the productivity of that fishery would implode. It wouldn't be very good, and that this also was timed with unusual weather, and that usually kicked in around Christmas time. And so Catholic nation, Christian nation, Christmas, a big part of their cultural tradition and heritage and all that good stuff. And so because it fell near Christmas, the Christ child, El Nino, the Spanish for the boy baby, that's where the name comes from. So that's why we originally started referring to it with this phenomenon. Okay, so so now we call it El Nino Southern Oscillation, or sometimes people just say Southern Oscillation, or sometimes people just say ENSO, all the same thing. Originally, we primarily talked about El Nino and not El Nino. Now we've more typically talk about we recognize three phases. There's the El Nino, which is that crazy time, which we'll talk about in a second, the hard deviation from quote unquote normal. There's the exact opposite, which is La Nina. So the opposite was, instead of the boy baby, it's the girl baby. And then there's just the regular times. Okay, so this is what, let's go over real quick so that we have we can remember what it was, or if you guys haven't heard it in detail, you'll get it. So what we're looking at here in this image, this is a cross section of the Pacific Ocean. I should say, so this is a Pacific Ocean phenomenon, particularly the southern part of the Pacific Ocean region. We now have come to understand, since this and all the meteorological and physical oceanographic research has shown, that similar things happen in other ocean basins, but the Pacific Basin is the big mother, right? The Pacific Basin is the big beast. And so while similar things, North Atlantic oscillations and things can happen, really the end all be all is what happens in the Southern Pacific. Okay. So here we go. So we've done a cross section, if you guys are with me. So over here on the right-hand side, this is the continent of South America. On the left over here is Australia, Indonesia, that region of on the other side of the Pacific Basin. And so this is a cross section. And so what we're looking at here is the black line is the surface of the ocean. Then as we go down towards the bottom of this figure, we're going farther into or deeper into ocean waters. And what is being shown here in cartoon form is the temperature of the water. And so temperature, remember, is thermocline, just refers to a rapid change. So a quick turnover in whatever the substance is. In the case of temperature, that would be a thermocline. And so that's what we're showing. So salt water, lots of structure. We tend to think of the ocean as this, a bowl of water or a bathtub of water or something, but in reality, there's massive structure in there. So to our human eyes, we sometimes just see water and assume it's all the same. There really is massive, clear pockets of water of different density and all currents and all these crazy cool things. And so, okay, so here we go. So we'll start with the neutral time, or the quote unquote normal time, right? So in the normal time, we generally have winds sort of gently blowing this away, okay? And by gently, I don't mean a wind going over, but the average, the net movement of air on near the surface is going to go roughly from, you know, these countries in South America over towards Australia, Indonesia region. And as you can see here, we have relatively cool water up near the surface. And as we on South America, and as we go to the other side of the basin, it's relatively warm water. This situation is why those anchovy fisheries are so, and anchoveta, I should say, and fisheries are so productive. Why? Because our default is to have a little bit of gentle wind coming off of the continent, and just like you can imagine, if you had a bathtub and had a hair dryer, if you had a coffee mug and you were blowing on the top, as you blow and move that surface liquid to the side, that's going to act to create a little bit of motion. And as those water molecules move over and pile up on the other, say, side of your mug, stuff from below is going to come up, and that's what the default condition is. So this is why this is one of the most productive fisheries in the world. We have cold, nutrient-rich water down here. Hopefully you guys can see that. My silly Zoom is putting things in front of me when I move my pointer. But basically on the lower right-hand side, bringing up this oxygen-rich, nutrient-rich water, oh my gosh, into the sunlight, into the shallow waters. Oh, plankton, phytoplankton, damn, I'm gonna go crazy, boom, bloom. Then all the zooplankton that eat the phytoplankton, damn, I'm gonna go crazy, eat all the phytoplankton. Then the fish, like the anchovetas and stuff, like, damn, there's all this food. So it becomes a very productive place. Okay, so that's the default condition. Okay, what happens in an El Nino? An El Nino is the breaking down of that system. So now Sabrina mentioned, oh, isn't it whatever, something that starts over here? As with so much of our climate system, we don't fully understand it. We're getting much better in terms of these models to say, if temperature is this and the winds are like this will probably happen. But as to the specific causal factor, we don't really understand that. If you talk to an atmospheric person, a meteorologist, they will say it starts with the ocean. The ocean is the spark that starts this cycle of events. If you talk to an oceanographer, they will say, oh no, it's the air, it's the atmosphere that starts it. So chicken and egg, but somehow, for whatever reason, this starts to break down. This happens every 7 to 11 years ish, sort of on this kind of scale of periodicity generally. And so going along, normal year, normal fish, etc. And then this pattern breaks down. What we see here now, again, the same thing, cross section. Now, instead of that warm water pile, and I should also say, this is cartoon version, but in addition to the warm water being concentrated, also the surface of the ocean is actually literally just as if you were blowing on a mug of coffee or something. The water is actually also piling up. So right here, as this wind blows, we're getting a little bit of lumpiness of the ocean over here. Okay. As we proceed into a classic El Nino situation, the winds break down. So the winds stop being as strong, and then this water that's over here, this warm dome of water, just like if you stop blowing on that cup of coffee, all of a sudden the coffee that's piled on the opposite lip will kind of slosh back. And so that's what happens. The surface water sloshes back. This warm water sloshes back, and we get these tongues of hot water that come across over the course of months the Pacific Ocean and bang into our sides of the continent, the western edges of these continents. What does that mean? Well, it has all kinds of implications biologically. So for example, in this case, it means now we have this lid of warm water. So if you're surfing, or if you're swimming, the water is going to be a bit warmer, so that's nice. But if you're those plankton, looking for your nutrient-rich water, not as much. So you're not going to grow as much. It's not going to be as many of you. So there's not going to be as many of your predators, the zooplankton. There's therefore not going to be as many of the fish individuals that the fishermen are going after. And so that's, and then in addition to that, we're also going to change where moisture is concentrating and how much water these clouds in the atmosphere are holding or carrying. And then La Nina is just an even more intensification, essentially, of that normal, in the sense of the winds are stronger, et cetera, and we get more piling up than quote unquote normal on the other side of the basin. We first figured this out with over 100 years ago with people sending balloons and things up into the atmosphere in and around Australia. And so it took a while for us to piece this together, but we now understand that the stuff that happens in a linked climatological system, the things that happen on one side of the earth affect things on the other side of the earth. And so here's another cartoon sort of illustrating the normal conditions. So the normal conditions, we have all the, again, warm water, piled up water. We get a very clear differential here, right? And we get hot, wet air, lighter than the surrounding air. And so it's going to tend to rise up. And then we get the circulation we're typically familiar with. Now, because of how the Earth spins, and we have a stuff called the Coriolis effect, really the exact equator isn't super strongly impacted. Instead, the areas to the south and to the north of the equatorial zones are really the ones that bear the brunt of these shifting weather systems. And so during an El Nino, what we get is we tend to get much wetter. So meaning we here in Southern California, and California in general, tend to get much wetter periods, okay? And so El Ninos are flood times for us, are big deluge times. Those are the times we're gonna jam up and fill up the reservoir and all that kind of great stuff. And because we're talking about a climatological system, when we experience one thing, other areas experience something else. So while we might be getting flooding, other areas that typically get regular flooding or regular monsoons will lose that monsoon. So El Nino is a differentiating from the typical background condition. And El Nino La Nina is drier than normal, right? El Nino for us, we think of that in the southwestern US, wetter than normal. La Nina, drier than normal. And so generally speaking, in our part of the world, when we get El Nino, that's wet. The Pacific Northwest, warmer. And then the sort of towards the eastern seaboard, Midwest kind of area tends to be drier. And we see this again, we see these patterns showing up, and there can be huge biological implications in terms of the types of critters that migrate and overwinter and things of that nature. Suffice it to say, looking at these different periods of El Ninos, we can see very marked deviation from the normal patterns of rainfall and therefore flooding. Okay. All right, before we turn our attention back to our flooding specifically topic today, I'll just say that as with many things that we're learning about, the probabilities are changing, and how we're being exposed to these risks are changing as we go through time. So already now, the number, for example, as we're showing here, the amount of people, the population in potentially large flood areas or exposed to potential flooding is larger than it was when I was born. And as we project into the future, that's going to continue. So also important to just put a pin in it to remind ourselves that we have to be really careful when using historic numbers or historic predictions as we start going farther and farther into the future to try to figure out how we want to plan for our cities, how we want to plan for our water supplies, etc. Does that make sense? Any questions about El Nino so far? Is that a okay quick review?
I have a question.
Yeah,
I have a few questions actually. For this, Is it because of just like sea level rise? Because it says like change at +2 degrees and then at +4 degrees Celsius. Is that just because of the increased sea level? Yeah.
So absolutely, the coastal communities here, so the folks right next to the blues of the oceans, absolutely that can be impacted. They will be impacted by sea level rise, and that will make them more likely to be flooded. But this is talking about across the whole planet. So this is folks that are even far inland from the coast. So as we'll talk about in a second, it's a great question. I'm really going to talk about two different. I mean, it's all flooding, but I want to break it down into two different types of flooding. And we'll talk about coastal flooding next week. But it's a perfect question. This is flooding broadly writ. Everybody encountered.
So like rain, because of rain
Yeah.
and like sea level rise and stuff.
Yeah.
Okay, cool.
Yeah.
And then I have another question. You said that like oceanographers think El Nino is more because of like the ocean changes first. I don't know, it just seems to me like looking at your diagrams and stuff that it would be a weather change first. Like
You mean atmospheric change?
Atmospheric change first. Why would they say it's like an ocean change first?
Because it's like something I would say, because they don't know. And so the water people are like, what the hell? It must be the air, right? And the air people are like, I don't know, it must be the water. And then because they're building, because we don't fully understand it. And the reality is it's constantly feeding back on itself, right? We're never starting from zero. We're just, the whole game is playing all the time. And so if you're an air person, you're going to focus on how the chess pieces move in the air, and then your start is just like, oh, we start at Monday at 8, right, or something. And so they pick water because they don't understand the water, so then they can blame it on the water people, and the water people are just the reverse. So they make all their cool models and their awesome simplifications of nature and all this cool stuff, but then what's the actual pook, what's the domino pushing to start it? They're like, I don't know, it's got to be the atmosphere people. So it's just a human nature kind of thing, why everybody blames one another. The reality is everybody acknowledges we don't fully understand why, but the reality is they feed back on each other.
Gotcha, thank you.
Totally. Good. Other questions or something else I wasn't clear about? Okay, cool. Okay, so Gabby had a perfect intro. It was almost like I paid her or something. Perfect intro to talk about this. So what is a flood, right? So when we say flood, what do we mean? And so for our class, flood is just you're underwater, basically. Something is submerged. But in a logistical sense, I want to distinguish traditional or typical or stream flooding from coastal flooding. And so today we're mostly going to talk about the stream flooding. And so what do I mean by stream flooding or traditional flooding or regular flooding or whatever term we want to use? We're talking about, generally speaking, it doesn't have to be in a channel, but generally speaking, we're talking about something near or associated with a channel. It could be a lake, but generally we're talking about channels. And so it's a relative elevation of that water level such that it jumps out of the typical landforms that hold that water. So if we're talking about a stream, it's going to jump out of the banks. If we're talking about a lake, the water is going to rise beyond the edge of the beach of the lake, that type of thing. In contrast, and that's brought about by precipitation, right? Other factors too, but rain, it could be snow, but basically we're talking about rain is what's going to trigger this. Coastal flooding can also be caused by rain, but it's not so much about stuff coming down from a higher elevation to us. It's going to be about the ocean surface itself rising up more typically. And so coastal flooding is going to be a situation or occurs when we have the situation of the supralittoral, which is the area above the highest high tide that we typically get. So the area above that, above the mist of where the waves break, when that area gets inundated with seawater, that's what we mean by coastal flooding typically. And just like Gabby said, absolutely, sea level rise is making this more likely to happen, and is, you know, the ocean level is getting higher. And the drivers typically of coastal flooding are going to be a cyclonic storm, so hurricane, something like that. It could also be a really, really low pressure situation far off, for that's sort of stable for a long time. Yeah, so those are the main drivers. So I have a couple slides in a second to talk. There you go, right there. That's what I wanted to say. So our default flooding is typically brought on by rapid bringing of precipitation into the system. So that's going to be either classically a thunderstorm, a summer thunderstorm, for example, or rapid melting of snow. Again, also in our changed climate, we historically snowed, in the classic conditions, say in the Sierras, was that snow stood there for, or rested there in that mountain meadow or something for a long time, and then slowly typically melted. Now we're getting much wetter snow when we do get it. So it's got a lot of water in it, and it's much easier to melt because of the nature of the snow that's accumulated and the atmospheric temperatures. And so we tend to get that snow melting much faster, as opposed to a little bit at a time. It comes out more, and it's more likely to be a flooding type of situation. And so in our part of the world, we're typically going to get flooding in spring and summer. So spring, the spring runoff, summer, those thunderstorm situations. The other broad category here of things that are going to trigger flooding would be, again, for us in our part of the world, atmospheric rivers. We'll talk about that in a bit, but that's going to produce mostly winter flooding. Okay, and then with coastal flooding, we have winter storms. It most typically happens when we have winter storms and king tides, or the highest of the season, of the month, or of the season tides. And so when the sea level is already high, and then we get some additional elevation added on top of that, that's when we're going to get those that flooding. And so here I say winter storms plus king tides or sea level rise. So we see this, the classic story is in Miami, which what everybody talks about. So even without a storm, we can get coastal flooding just with the king tides now, because we've seen so much sea level rise. And so indeed, people are now using events like a winter storm plus a king tide, and maybe some of you have taken part in this, but we have various citizen science projects where we wait for a winter storm with a high tide, and then everybody goes out with their cell phones and they take pictures of the Ventura coastline, the LA coastline, the San Luis Obispo coastline, San Diego, wherever, and we take photos, and then we upload those to a server, and people look at our predictions for sea level rise, because the winter storm is, in a sense, jumping us forward a decade or a couple decades, depending on what the storm is like. So we can get a visual sense of what the inundation is going to be like. And then again, the other source of coastal flooding is going to be these big cyclonic storms, so tropical storms, hurricanes, that kind of stuff. And those will typically, coastal flooding from those phenomenon in our part of the world will typically happen in summer and fall. Okay, so again, flooding, coastal flooding, we're mostly gonna not be focusing on coastal flooding for the next bit here. Does that make sense so far? Questions? Okay. So what's driving the flood? And so this was also a great lead in for this thing that Gabby was mentioning. So we have the meteorological drivers, the drops of rain coming and hitting the ground, for example, and we have the stuff that we are doing as a society to make flooding more likely. So meteorologically, we're talking about lots of rainfall over a broad area is one of the key drivers we'll typically see, and we start to get worried about flooding happening in the wake, or maybe more localized rain, but really, really intense when it does dump. Similar rapid melting of snowpacks, and then the buildup of temporary dams, or what can be referred to as jams, either from ice or from debris. So in the wake of a wildfire, we have all this crud that, you know, burned dead tree trunks and stuff like that. And then they sort of fall down the hill, or it rains, and the rain brings down some of these boulders, trunks, etc. They start to go down, 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 and they get lodged somewhere. And then just like like a beaver dam, that they create this obstruction, and the water piles up behind them. And then it's just creating a huge mass of water, a big weight. And at some point, something happens, one of those tree trunks snaps or whatever, and all of a sudden this whole chunk of water comes down very, very fast. So that's again, that's what happened in Montecito in the wake of the Thomas Fire, and we just see this over and over again. Now, that's been going on forever. The complicating factors that we've brought to this is that we've done a lot of constraining of our waterways. So the typical story, right? River or rains, water goes in the channel, goes downhill, and then if there's a lot of water, the flooding event is that water jumps out of the channel, or leaves the main channel, slows down, spreads out over the floodplain. We, as a people, have gone in and basically put dams on the side of those rivers, so we've not allowed the water to jump out, because we've decided in the last 100 years or so, especially, that we don't like that we want to tell the water what the water should do. So we've constrained our waterways, we've armored them, we've put concrete in them, and we've raised their edges, raised their sides. We've also done a huge amount of so-called impervious surfaces, concrete. Think asphalt, think parking lots, buildings, things of that nature, such that before, when it rained, this area was all soil. And when the rainfall hit, the water could relatively quickly, go into the groundwater, filtrate through the soil, get to the plants, etc. Now we have all these impervious surfaces, so as the water strikes that surface, there's nowhere for it to go, so it rushes off and produces more flooding conditions. The same thing happens along the coast. We just have seawalls, but it's the same idea. And then we have dams and infrastructure that are not necessarily the most robust. So I just had my sabbatical last year, but the sabbatical before then, I was in Turkey, and one of the main things I did there that trip was to assess a bunch of dams and look at the ecological consequences of these dams. And when I was there visiting, I should have actually put pictures in my talk about this, but anyway, when I was visiting these dams, some of them which were just built. In fact, one of them had been finished like 6 or 9 months, something like that, before I got there. Massive cracks in the dam. It looked like something that was built 200 years ago or something. It's like, dude, you guys just built this? So our dams and infrastructure in contact or proximate to the water flowing and water movement aren't necessarily super robust. And so those can fail catastrophically. And then with all this stuff, as we constrain the waterways, as we do all this stuff, we trick ourselves, we fool ourselves. We say, dude, totally safe, it's all good. I'm gonna now move into here. I'm gonna now move into the area in Ventura around the Ventura River and the Santa Clara River. In the San Francisco Bay Area, we're now gonna move into East Palo Alto, and on and on and on. So once we've created this situation that temporarily looks safe, we then start putting businesses, homes, recreation, all these different activities in the floodplain that are now vulnerable to flooding. Whereas if we had not had that infrastructure and the area routinely flooded, of course, no one would put a house in that area or in that spot, because they're like, no way, dude, I'm not gonna put my house there, it's gonna be flooded. Okay. Okay, so there we go. So another frequent distinguisher in terms of, and I'll have some other terms, some other flavors of floods, but I would say probably the most common risk, when we talk about risks of flooding, the most common categories when we're talking about these traditional types of flooding are going to be the regular quote unquote floods and so-called flash floods. So flash floods are very fast. They start up really quickly and they dissipate really quickly. The technical term, the meteorological term, is that flash floods happen within 6 hours of a rain event starting. Usually it can be a lot faster, within 3 hours than 2 hours kind of thing. It's going to depend on the lay of the geography of the system, but basically it starts to rain, boom, time to get messed up. And if any of you guys have done any hiking in and around the American Southwest, those beautiful sandstone canyons of the Canyonlands and the Mojave and all these great places, that in the summertime, when it's great to go out there and check them out, these areas are very, very dangerous to be in. Again, because we tend to have in the Southwest, we tend to have these thunderstorms, afternoon precipitation events. And if they park over one of these little arroyos and they start dumping and you're in there, you can, drown very, very quickly. And many people do every year. So flash flooding. So flash flooding happens very quickly. And it doesn't necessarily have to be in a stream channel or in an arroyo or something like that. They can happen just if there's enough dumping, they can just move over regular surfaces. So they don't have to be in a channel. And then that's going to be contrasted with more typical flooding. Flooding is usually a longer event. So it takes a bit longer to get going and it lasts longer. So whereas a flash flood, we're usually talking about minutes to hours. With a flood, we're talking more like days to weeks, and in some cases months. Although typically not months, it's typically days to weeks type of thing. They're very powerful, these flood events, right? So here's a couple examples of from West Virginia where just things are completely hammered. So this house, there's almost like an earthquake hit this, or maybe like a semi drove into this house. This was all water movement that destroyed this house. And depending on where we are, we can get high water levels, tens, easily over your head. And potentially, over your first story of your house or second story of your house. So these are really very, very powerful, very, very strong events. These have been going on around the world. One of the most craziest situations happened in China in 1931. So this is the sometimes people call this the Wuhan flood, but basically this happened throughout huge swaths over thousands of miles of the country of China, and essentially the Yellow River, all these rivers, we just got lots and lots of rain, and it never let up. It was rainstorm, 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 rainstorm. Started in the fall, and it lasted up until spring. And so these are some images that just show that, again, sometimes when we think about one thing, we don't really think of the other. So when we think about wildfire, we don't necessarily always think about the problems of flood, but they're coupled. Same thing with floods. Once we have floods, a lot of times that will induce some type of failure of heat generation, electrical generation, whatever, and trigger fires. And that's what you're seeing here. Whole massive areas of the country were submerged for months at a time. And because a lot of these floodplain areas, these were a lot of poor farmers, there weren't big skyscrapers around or big mountains necessarily right nearby or something. So a lot of folks didn't have anywhere to go, and so they concentrated in where they could. And a lot of people just ended up living on boats and making boats essentially their homes for weeks to months on end. And that's what we see here in this picture, where we have these huge numbers of folks that are essentially in a floating city, because so much of the area, their food is messed up, their homes are messed up, etc. And while the numbers are hard to estimate, some of the numbers say as much as 2 to 3 million people died in this flood. So this was a massive event. And so as with many of our disasters, it's not only just the initial raising of the water, but it's also all the knock-on effects. So in this case, it was the some people just drowned outright and everything, but most of the folks were dying because of disease, dysentery, things of that nature, or simply not having enough food. And actually, this picture is taken by Charles Lindbergh. And so one of the first ways that the Western world figured out what was going on was Lindbergh was doing a tour, a visit. I can't remember what he was doing, something in Japan. And so when this broke out, he and his wife jumped in their plane, a seaplane, they flew over. And this is one of their photos, and their photos, which got into the Western press and led to a big fundraising effort and awareness to try to help folks. But for example, they first landed their plane, and they had brought a doctor and some medical supplies. It was a little plane. What could they bring? Not very much, right? But they got out of the plane and they're telling people, hey, here's some medicine. And they were like, screw that. We need food. We're starving to death. So so these knock-on effects are quite real. So again, like in the China flood, there can be very large, persistent events. Also, these flooding situations can be very tight and very short, but still very powerful. So here's a crazy video I'm going to play for you guys. So this is from Argentina a few years ago. So these are some folks on a hiking expedition, and they're going from the right to the left, right? They're in the mountains. So these guides are all responsible guys, and they're helping them across this little rivulet. They're on like a 3-day trek or something like that, I think. So the guides are helping them up. So popped up really fast, right? Super fast. And now almost just as fast, it's dying back down, right? So this is a big boom, boom. So thankfully, none of these folks were hurt, right? They had smart guides and they were paying attention. They were looking upstream when they were doing this crossing. But even experts like this, even people know what they're doing, have to pay super, super close attention in these situations. Another plug comes through. And again, those boulders are like, those boulders are from basically chest size to body size boulders. So very powerful. Questions?
I would have ran so fast. I'd be like a little speck out in that field. Like I would have kept going.
Totally. And it's just a reminder that we do all this safety training. I hope you guys, I know things are a little weird. I hope you guys are taking wilderness first aid right now. If you're not, take it in the fall. I want everybody to take that class. It's part of our field professionalism series taught by Ben Kuo, the awesome Ben Kuo. It really can help, not just with dealing with things like that, but all kinds of manner of stuff. You guys get safer and you know how to comport yourself. And again, very soon, once we're back to being out and about our normal ESRM ways, when we do all of our field stuff, we also really pay very close attention to make sure that we're always safe, you're always safe, and we're out doing stuff. But it's always important to make sure that you have safety first and foremost on your mind.
That's
Okay,
great.
yeah, go ahead. No, go.
I was just doing a really cool course. I didn't even know like that was offered. I took a wilderness first aid to get certified, and I was like, that it was a whole weekend, but they go over all these different scenarios, and they make you think of to take stuff in your pack that you would never think of, but then you're just like, oh wow, like, this could be really helpful. Oh, so I was just
Totally.
like, I need to do mine. Yeah.
Totally. Yeah, no, I completely agree. It's one of those things where you know, some classes we take because they're interesting or because we have to take, or you know, it could be cool, or you know, that's good to know. And there's others that you'll just use all the time, you know, all the time. And I think and you know, I would hope you guys would say disasters would be one of those classes, but you know, I probably not. But definitely, Dr. Ben's class is one of those ones you can use every day. Yeah, Sabrina.
I worked briefly for an ecotourism company up in the mountains here, and I learned really quickly to not always trust the people that you think are responsible for things like your safety out in the wilderness. Like my boss that I worked for, I quit after I think it was the third day because we were doing river crossings, and it was my first day doing the river crossings with them. And after the first stream crossing, he was like, okay, I saw you do that, you're good. And he left me to do another 6 hours of hiking and other stream crossings by myself. And it was pretty crazy.
Yeah, so good for you. I mean, you are all responsible for your own self, and especially when you guys are, you know, you're kind of young and you're starting a job or you're starting this career or this thing. It can be really easy when you have a supervisor like that, or an old fart like me who's like, just go do it, you'll find. And you really do have, when it's something, you know, if it's making a map on GIS, whatever. But you know, if it's something where you are, you know, your life might be threatened, or more importantly, people that are that you're in charge of might be threatened, you really do need to have the confidence to say, yeah, no, this thing ain't happening. So I'm glad that you had the wherewithal to say, yeah, this ain't cool. I'm gonna bail. So cool. Yeah. Any other thoughts on that crazy video or related subjects?
I had a question on flooding itself. Is it safe to be in a skyscraper when a flooding is going on? Because it wouldn't seem very safe, right? I think a house would be safer than a skyscraper because I don't know. A skyscraper could.
Sure. Yeah, I mean, I would say in most cases, the higher the safer. If we're talking about just a traditional flood, you know, if we're talking about an earthquake or something else, maybe there's other considerations. But generally speaking, most people are going to die because they don't understand how quickly the water can rise, you know, how fast. And so generally speaking, by definition, a skyscraper or a high rise, you're going to be farther off the ground. I would rather be in a, you know, third story, fourth story elevation than on a first or second story. And one of the main killers of people actually in floods are people in cars. And so they look at it, they kind of say, oh, it's only, well, I don't know, you pick a foot, 2 feet. It only looks like it's a foot or 2 feet or something like that. So I could probably, and it's relatively narrow. It's just the street, right? So I can come from my driveway and go across and go to the other avenue or something. And that's where almost everybody gets into serious trouble. So generally speaking, when you see flooding events happening, you want to get as high as possible. Where this most matters, I think in most floods, Ali, it probably doesn't matter, but where it really matters is with tsunamis. That you can have, you know, so tsunami is kind of like that video we just saw, but instead of the water being, you know, constricted to a channel, it's sort of like from horizon to horizon, like everything is coming up. And for example, with the Fukushima story, a lot of people didn't get high enough quick enough. And so with the tsunami, a lot of people were curious and they were looking at it, or they were on low slung buildings and they were hanging out there and they were videoing it because like, oh, this is crazy. I'm going to look, there's a tree coming or there's a car coming. Like, wait, there's a tree coming, there's a car coming. And by the time they really realized what was up, the water was up to that second floor of the parking structure or something of that nature, and they were trapped. So people that were in buildings that they could go higher in, those folks mostly survived that coastal flooding in that case.
I see, because it kind of like the Boxing Day tsunami, how there's so many videos of it. It's kind of like shocking how, because there's videos of people at resorts just recording out of nowhere, a tsunami comes in and it just destroys everything. Then at the last second, everybody's panicking.
Yeah, it's very, yeah. So I should say that video, I showed that video because one, it's just insane, but two, everybody was okay. So I wasn't going to show you something that people were going to die in or something like that. But it's unfortunately very common with some of these very intense disaster things nowadays. So back in the day, we didn't have videos, right? It was you have to rely on a TV news crew that happened to be doing a live broadcast or something of that nature. Now, because so many of us have our video cameras with us, we get a lot better video of stuff, but it also means we also unfortunately capture some very tragic images when people are very stressed out. Okay, so we're doing great. Other questions or other impressions? Okay, so we're almost up to our first break here. So we'll just go through this slide. I don't like this slide now, and then I look at my slide. I think it looks really lame. I think it's too many words. Anyway, so we'll hit the slide, and then we'll take our 10-minute break. So some other common variants. Again, the main breakdown I want to talk about, or like you guys think about, coastal flooding versus regular flooding or standard flooding. And then within that standard flooding, it's really the biggest risk is flash flooding versus more traditional flooding. But these are some other flavors that you might encounter or see referenced. River flooding, this is basically this is what's gone on forever, right? This is the classic flood. This is the water jumps the bank and hits the floodplain. A coastal flood, as we mentioned, are driven primarily by low pressure cells, cyclonic storms, and to a lesser extent, tsunamis would trigger a coastal flood. Urban flooding is increasing, right? Urban flooding is of all these categories here, urban flooding is probably the one that's increasing the fastest. And by urban flooding, the classic thing would be something like downtown LA, but this really refers to any type of urbanized landscape. So it doesn't have to be a pure concrete jungle. And what we've essentially done is we have, again, made the surface impervious. And some recent studies are suggesting that on average, these areas in human-dominated landscapes are something like 2 to 6 times more likely to throw off dangerous amounts of runoff, meaning that stuff that would become the floodwaters relative to the natural landscape before we'd put those buildings or those concretes in. Flash floods, as we mentioned, classically these would be in these small narrow channels, an arroyo or a wash, and then jams. So we can have ice jams, we can have debris jams, and you'll hear people refer to all these types of things in different flooding situations. Okay. So I think with that, I think we'll pause and we'll pick it back up here. So we'll take a quick 10-minute break. You guys stretch your legs. I'll pause our recording and you guys take a stretch, and I will see you all back in 10 minutes. Ready, set, go.
Literally, we're switching from male to female, female to male because
Totally.
of the nutrient or the pesticides.
Yeah, totally. Yeah, so
Thank you.
So yeah, no, you're welcome. You're welcome. Take my coastal class or take our coastal contaminants class if those things are of interest to you. Okay, great. So let's any other questions before we get going? Okay, so let's keep going. So delving deeper into flooding, a couple some key dimensions here. The first is we think about flooding, the intensity, which is going to refer to how much rainfall is happening. So how intense is that storm, right? And then duration. What's the temporal period over which that dumping occurs? We already mentioned the difference between flash and regular flooding. Another key dimension here to flooding is how big an area is this rain falling over. So different terms here, but all related to one another. The area that we're capturing those rain droplets or that precipitation. So you can call it a catchment. If it's bigger, we call it a basin. Usually the common terms now we use are watersheds, but it basically means the area in which when a bit of a molecule of water, precipitation falls, it's going to be channeled to a certain location. So all the area in that catchment or that area is going to be important. So you can imagine if we're in a small little mini canyon the size of our house, not that big a deal, maybe, right? Whereas, and we can't get that much rain jammed up in there. Whereas if we're a watershed the size of the Oxnard Plain, it's going to be much easier to get potentially a lot of rain from a storm cloud parked over there, and then something even larger, the Santa Clara River watershed or something. It'd be even easier to get potentially huge amounts of water moving through that system. We articulate flooding and channels with
Professor?
Yeah.
Are you sharing a screen with
Oh my
us?
God. Yes, I am. Totally lame.
Okay.
Thank you. Man,
Yeah.
thank God you guys are here to help me do my recordings. Otherwise, I would just be doing the whole thing. How about that? Can you guys see that now?
Beautiful.
Oh my God. Whew. You guys saved me again. Okay. So yeah. So oh man, now we jumped all the way to the start. So yeah, okay. So these are just some key terms that I wanted to touch base and make sure that we're thinking of here. Okay, so intensity, rate of rainfall, duration, how long it lasts. We already touched on the flash versus regular flooding, and then the area over which that rain precipitation is going to be captured. And then stream gauges. I always misspell stream gauges, but I always try to probably put a U in there, but this is how you properly spell it. But a stream gauge is an engineered structure that we can use to consistently measure water in a channel. The one I know best is the one right there if you're on Lewis Road and you're driving into campus, not on the new CSUCI entrance, but the road Camarillo Street, the one that goes closest to University Glen. As you come over that road and as you cross Cayugas Creek, next time you're coming into campus, if you look right to your left, right there at University Park, what we call Cam Park or Camarillo Regional Park, you'll see a cylindrical structure and a sort of little wooden shack with a antenna on it. That's a U.S. Geological Survey, a stream gauging station. And so every minute of the day, that sucker is recording what the water is doing in our channel in a stream gauge. So that actually has some wires that go down to the stream gauge itself, which is in the channel, and it's recording these different dimensions of the water in the channel. Key measurements here are going to be the water level or the stream stage, so how high the water is, and then the discharge rate, what the volume of stuff going through there is, the rate of movement. In the US, because we're super weird and silly and all this kind of stuff, we use the common term you'll see is CFS, cubic feet per second. So that's going to be the amount of water in a 1 foot by 1 foot by 1 foot cube, or the number of 1 foot by 1 foot by 1 foot cubes that are going to go past this area per second. The rest of the world uses cubic meters per second. Same idea, exactly same idea, just obviously different units. So stream gauges measure the water height and how much water is going through that area. The goal of our exploration of what's going on in these systems is to look at peak flows or peak stream flows. Peak stream flows are then going to, because obviously peak, the greatest, that's when we're most likely to see flooding and or the most problematic level of flooding. We typically see So this is some graphing of some of the largest floods that we've had in the world. And what you see is not surprising. So first, I'll just note this is a logarithmic scale, right, on both these axes. But basically, as the area, as the catchment gets larger and larger, the discharge gets larger and larger, right? So there's a relationship here. Now it's not one-to-one, but overall, as we get a larger area that we're talking about, we're more likely to get more damaging floods. As we've touched on some of these, but these are all elements that can contribute to flood problems. The shape of the stream, if we have a controlled freshwater system managed by dams, the release of water from dams can be an issue. How steep is the slope? Is there vegetation on the slope? Has it been devegetated, etc. So all these things can influence the occurrence of a flood and the duration and the intensity of a flood. So we have a stream gauge, let's say in the channel or whatever. What's that gonna measure? So this is gonna help us understand how floods happen. And so let's look at a hydrograph, which we can generate from that stream gauge. So a hydrograph, hydro water graph, so water over time. And here we see on the x-axis, here we have, going from time 0 to time 1, or time past to now. And then we have the discharge, which again is the volume of water. In the US, we'll use typically CFS, cubic feet per second. And right here, this would be the rainfall. So this first little graph would be something, maybe a stream gauge up on the hill, or something, not a stream gauge, a rain gauge up on the hill be recording. And so you dumped a lot, and then maybe that mass of clouds moved on, it rained a little bit less, and it rained a little bit more, then it stopped. There's going to be some lag time between when the rain leaves the clouds and strikes the soil surface for it to actually dribble down and eventually get into the channel, etc. And so we'll see this event where there's some amount of lag time, and then we hit the peak of the flow in the channel. This first one here would be an example of one that we had. I don't know, this is sort of just a cartoon here, but a relatively large lag time. The one on the bottom is a relatively smaller lag time. Note that if we had the same exact volume of water entering the system, in some thought experiment here, if it's going to come quicker, the peak's usually be much higher. So the total duration will be less, but the peak stage is going to be higher. And that's just a physics thing. That's just squeezing a same volume of water into different places. And this is what we typically will see when we are looking at these discharge figures. So again, this light blue is measured differently. So this light blue would be measured at a rain gauge somewhere nearby or in the watershed. And this axis here, rainfall, is referring to this light blue stuff, these bars. Or you can call this the y-axis. Some people call this the y-axis, this other axis here. Notice the units are different. Here's 60, here's 40. So in this case, we're showing the discharge volume, right? So here we have the volume of water in the stream. So this axis, this thing is in the watershed. This axis, this thing is in the channel. What we see, a couple examples here are, again, we know that there's a lag time. The lag time is going to be the difference between the peak rainfall and the peak discharge in the stream. Knowing that and having some data on this can help us predict, so if we understand that this system typically has a 5-hour lag time, right? We're probably going to have a response to that that's different than a system that has a 2-day lag time, right? And so the 2-day lag time, we have more time to get people out or get those warnings to people or evacuate people or what have you. With just a few hours, you don't have much time at all. And so understanding these hydrographs will help us understand the risk and help us better plan for avoiding the worst outcomes associated with flooding. Okay, and then we just have the rising arm. Typically, the rising arm tends to be sort of a more gentle rise. Bankful discharge. This is where, in this case, in this particular system, this is where the water is within the contained edges of the channel, the primary channel, either the natural channel, or if we've levied it or something of that nature, the area where the water is contained. Once we leave the bank full discharge, then that's when the water jumps out and goes into the fields or goes into the city or what have you. And then usually, not always, but and again, this will depend on the system, but oftentimes the reduction phase tends to happen a little bit faster than the rise. And again, and we just use this over and over again. This is last was sort of a cartoon example. This is a more realistic example where we have rainfall data, and then we can plug those into flooding models, and we have the actual measured, in this case, the actual measured water in this particular river in Australia, and then the modeled one. So the model is the purple is what we predicted would happen, and the green is what actually happened. That's pretty good, right? So when we have good data, we can do a decent job, and we know the conditions of the system. We can do a pretty good job at estimating what the flow will be like, the timing of the flow, etc. And I'll just also note before we get back here to say that this figure is for a particular point in the river at mile whatever. So let's look at an example here. In this case, this is from the East Coast. But here we have this area in red with the red dot and this area with the blue dot. Now this is all, notice, this is all on the Savannah River. So this, I don't know how you say it's down, Clio, I think, could be Clio, I don't know, Clio. Clio is on the same, river channel, the same water element as Calhoun Falls, right? The difference is Calhoun Falls is much closer toward the headwaters. Clio is much closer to the mouth of the terminus of the river. And so what we see here is from the same, this is one storm, right? So this is same place, but notice the hydrographs are quite different, right? So here, the red is this guy and the purple is this guy, right? So this headwater responds much faster, right? Much closer maybe to where the rainfall storm happened. Boom, boom, and drops out, yeah? The farther down, it takes longer to get to that peak. In this case, this is in days, but the units don't matter that much. But right, so days here, and the peak is much higher. So so you have to move much faster if you want to save your house in Calhoun Falls, but you don't have to. You have to move faster, and also it will resolve more quickly. But also there isn't going to be as much damage, whereas down here it's both much higher water stage and it's going to last for much longer. Natural floodplains are great. Natural floodplains are one of the best instruments we have to deal with flooding. Again, this is a natural part of the system. The ecosystem has evolved with this. The deposition of sediments, etc., throughout this area are important for the healthy functioning of these ecosystems, and on and on and on. What we'll typically see in a natural channel is a lot of sinuosity or curviness or bending of the river structure, and natural changes over time, and movement of this channel here from this bank at some point to this bank over here. In the case of the Oxnard Plain, the Santa Clara River, over the course of its history, has moved from basically to where campus is, basically the Cayugas Creek Channel, all the way up to Ventura. So the Santa Clara River has moved all the way across the Oxnard Plain. That meandering is a natural, healthy thing. We humans tend to not like that. We humans tend to go, no, I want to constrain it. And so we tend to modify the channels and the floodplains. And the most common way we modify things is to constrict the flow and contain it within a certain area. We do that with levees. Again, a levee is like a dam. It's just, whereas a dam would go across the flow, levees parallel the flow. And the idea is when we do have that flood, the idea here is to keep those floodwaters trapped within this area and not allow the floodwaters to come over to where our barn is, or maybe where our crops are over here. Yeah, and this causes all kinds of problems. So here's a little hydrological animation. And so what this is showing is just movement in the channel. And so we can see elevation here. Here, green and warm is higher elevation. Blue is deeper depth into the river. And as we have a deep channel, which is analogous to having levees on the side, notice the water is flowing faster in this area. Here in the shallower areas, it's doing eddying and slowing down, et cetera. So the natural flood story is water's coming down the channel, jumps up. As soon as it jumps out of that channel, the flow reduces, sediments drop, water speed drops. As we constrain the water and force it to stay in this channel, we tend to artificially increase the height and increase the speed of that the flood, particularly seen as we go farther downstream. And so it makes sense, but I'll just make sure I state it clearly. The impacts of flooding are almost always worse as we go farther down the watershed. As we go farther down the water flowing, there's more impacts, more longer impacts, more deaths, things of that nature. The other thing that we typically do when we mess with rivers is, again, there's that natural sinuosity I mentioned, right? The snakiness of the river, and this is going to naturally change over time. So this huge oxbow here, maybe this is going to go, and then one flood event or something will happen, and this will break right here, and then the river will kind of go whoop and go here, and this will be sort of an orphan loop, and eventually start to sediment in, et cetera. So this acts to help, amongst other things, slow down the flows, right? As we channelize and as we straighten a river, this is done specifically because engineers hate water by and large, and they want to get water away as fast as possible historically. And so by making it straight, the water is going to go way faster, but it also is going to mean that if it does hit you, or if you are trying to ford the river or something, it's going to be going a lot faster, and it's going to be a lot more problematic. Again, this would be an example of a very flashy system, rains quickly and boom, quick floods, versus something that's a more much slower ramp up and and that water volume being extended over a broad period of time. Yeah, and we do various things to try to mess with the water and try to respond to these situations. So we can put in these different catchments or retention basins that act to sort of capture the water and change the speed, et cetera, and all with an air to reducing disturbance or reducing impacts. In this case, this is an area, we can see this is an engineered levee, right? So this is earthen, but people have driven bulldozers on it and stuff and sculpted it the way they wanted it to be. And this is sort of capturing this water, and then there's most likely some structure right here, a road or a something, bridge or something, and then we'll see these types of structures. And so historically, when we wanted to move the water from this area, we would use a horizontal culvert, right, a pipe basically. But we've realized that that's not super smart, because if we have a pipe laying horizontal and the boulders come down, boom, and they plug it up, we're screwed. So this is now the sort of state of the art of engineering of these types of structures, where we have an area, and this is just a pipe, but instead of being a horizontal pipe, it's a 90-degree pipe basically. So we have all these things. So if a big boulder comes down or a tree branch and hits this, bang, this is strong. So it's not going to plug it up per se. There's lots of ways water can get in. And then we have a sort of a rebar cap on top of this, so that water, even if debris comes in here, water can keep flowing through. And then after the storm comes through, or after the big pulse of the flood comes through, we can come in as humans and with engineering equipment, with excavators and things like that, and physically excavate this out. And so deal with trying to mitigate some of the flood impacts that way. Okay, so again, flood discharge is that volume. And so to know that volume, we need to know the cross-sectional area, right? So now we've taken this image of our stream, our river, where the river is flowing from your screen towards you, yeah? And so we have a bank on this side, we have a bank on this side, and then this is the bottom of the channel. The deepest part of the channel is the Thalweg. If you guys are interested in this, another great class to take if you've not taken it or haven't planned to take it, is our water resources management class, historically taught by Dr. O'Hyrick, now being taught by Dr. Fairfax. Great class, and they spend a lot of time going over all these measurements and all this great stuff. Okay, so we want to know this cross-sectional area, and what the discharge is going to be the flow through this blue area over time. So ultimately, all you really need to do is do some simple math. But again, if we had a natural channel like this, that can be really hard, right? Because we have to really accurately measure it. As I mentioned, stream gauges are an engineered structure. So usually we'll put something in the channel, a slab of concrete or something with a defined V or something, so that we know what the shape is. We've picked the shape. So rather than going and measuring the shape, we've dictated the shape, and then it's a lot easier for us to calculate how much water is going past point X in the river. Okay, yep. And so, yep, you guys can take our water resource management class if you want to learn how to measure that. Okay, so the next thing, does that make sense? Any questions about that stuff we've been talking about so far, you guys?
Real quick, I thought of one.
Yeah.
So you were talking about the 90-degree pipe.
Mm-hmm.
So would they have like multiple of those in the river, because, or just one? Because I guess initially I think like if there's like intense flooding or whatever, then one isn't going to do that much.
Totally, yeah. So they wouldn't typically put those in the river per se. Those are going to be more like the channel above the 33 freeway.
Okay.
The area above your the valley above your house, those types of things.
Gotcha.
You wouldn't put those in a typical main channel, but these are going to be in all these sort of tributary areas is where we'll see them. And again, they're usually going to be right before something we're trying to protect: a bridge, a road, a house, a barn, something of that nature.
Okay, thanks. That makes sense.
Cool. Okay, cool. So next thing I want to talk about is this notion of that we hear all the time in regards to flooding, and in regards to other things, storms and things too, but it's most popularly associated with flooding, which is this notion of the blank year flood. The classic one that we hear most is the 100-year flood. So this current phrasing, this current terminology came to us starting in 1973. And it's really about an effort to measure the recurrence interval of floods. Okay, again, we get to get a sense of what discharge is, what river stage is, all this kind of stuff. And then we want to know, hey, how often or do we have a problem, or when might we have a problem? Trying to predict this, trying to forecast, right? And so the idea here is, what's the recurrence of a flood? Is it going to happen every year? Is this going to happen every 6 months? Is this going to happen every decade? What's the deal? And the idea with this so-called 100-year flood is that a flood of this level, right, whatever the level is, the flood that would harm the city, let's say, we would have that level of flooding. We have a 1 in 100 chance of that occurring in any given year. That's what the 100-year flood means. Now, a 100-year storm, which is the rainfall event that's going to precede the flood, doesn't necessarily, we usually think of it as triggering a 100-year flood, and it could well, but they're not necessarily perfectly coupled. But usually, as we're at least initially starting to put our toe in the water, that's usually what we tend to think of. Oh, big, once in a century, if you want to use that terminology, rain event is going to lead to a once in a century flood, right? Seems to make sense. And for the last 50 years, people are like, oh, okay, I get it, right? And Joe Blow, when they read the newspaper or they look at the weather forecast, or whatever, they kind of think they understand what, once in a century, right? So what do you guys think? Do you guys think once in a century is common, uncommon? When you hear people say something like that, what do you think?
Are you asking if you think if it's common to hear people say that?
Yeah. Or if someone said, hey, this thing, let's call it a flood, this thing, it has a 1 in 100-year chance of happening, or once. So when someone says a 100-year flood, does that sound like a common thing, or does that sound like a rare thing?
Oh, I see what you're asking. It makes it seem like it's a rare, like it's not going to happen in your lifetime.
Yeah, everybody agrees that makes sense.
Yeah.
Yeah.
I agree.
Yeah, once in 100 years. It'd be great if we all lived 100 years to be 100 years. That'd be cool. But that's unfortunately, we're probably not all going to make it. So maybe it's going to happen when I'm not even alive, right? Or whatever. Okay, so there's several problems with this. And this is, I think, while there's all kinds of management issues associated with all of these disasters that we're talking about, when it comes to flooding, I think this is the most important challenge we need to figure out and to deal with when we talk about to the public, when we talk to homeowners, when we talk to just everybody. So can you guys think of some of the problems with that might be associated with using this 100-year flood measure? And I'm calling it the 100-year flood fallacy, so you can tell that I know that I'm signaling there's some problems with it. But can you guys think of what some of those problems might be?
Maybe people just, it'll kind of make them put off the idea that like a big flood could ever happen, right? Like you said, in their lifetime. So
Totally.
they don't prepare and they're not concerned about
Totally.
what happened.
Totally. Yep. That's the mother lode. That's the big one, right? That this I'm going to argue here, and in our readings, you guys will be reading about this stuff. But I'm going to argue that this way of presenting flood risk is counterproductive. It gives us a false sense of security. But why specifically might? So that's good. But can you guys think of some specific problems with this 100-year flood? Like why might that be wrong, or why might that be misleading to think about flooding that way?
People aren't going to like live their lives based on something that only happens once in 100 years.
Yep.
You're not going to change your infrastructure or build your society around a once in a century possibility.
Yep. Totally. Other thoughts or other ideas?
Doesn't it like suggest that there's not going to be more than one really bad flood in a given area?
Totally. Yep. Exactly. Yep. So we have a flood of that magnitude each century, right? Is the implication of that. And I think that's what almost everybody thinks when they
So then when one happens, then people are like, oh, we're good for 100 years. We'll deal with it in 90 years. We'll start planning for the next one.
Yeah. Yep, exactly. Other thoughts, other ideas, or other things that could maybe be problematic with that, or lead us down a problematic way?
Well, I had never heard of the 100-year flood until like last week in water resources.
Okay.
And I was so confused. I had to look it up to like wrap my brain around it because we didn't really like talk about it. And we were doing one of those graphs, like calculating one of them.
Mhm.
And I was like, are they saying like this? That's what I thought, like it's going to occur every 100 years. I was like, that does not make sense. How would it occur every 100 years? So I had to like look it up and like research it to understand.
Yeah, totally. Yes. Yeah. So well, it's great that we're sort of on the same page in these two classes. That's cool. That's right. So we're reinforcing each other. I hope this isn't totally duplicative of what Dr. Fairfax has been talking about.
No, it's really good. It goes hand in hand. It's nice.
Okay. Great. Excellent. Okay, cool. So here are some of the problems. Here are the problems with the 100-year flood. Again, what I call the 100-year flood fallacy. The first is that, as you guys identified, floods are irregular. And you guys might have heard of the law of averages, right? I'm going to call this the flaw of averages. So, and we touched on this a little bit with droughts and the problems, but it's the same idea basically. So here we go. So here's a stream flow from this is a figure from the USGS of this representative area. But check it out. So here we're going from back in the day, 1910 to the early 2000s. And this is cubic feet per second. So this is the flows, the volume in the stream. So you can see in this year we had this amount of flow, and this year we had this amount of flow. This, right? So it's a natural system. So there's noise. So some years we have lower flows, like in, I don't know, 1920 or something. And then in other years it was super rainy or super wet, and we had a big flow, right? And so about every 10 years, we're hitting above this level, right? So I said 100-year flood, but it could be a 10-year flood, a 500-year flood, a 1,000-year flood. We could pick whatever the denominator is. But what we see here is, okay, 10 years, but check out the 10 years. So here we go, 1910 to, this looks like 1922 to 3 to 4 to 5, 6, about 1928, right? So that's, about 18 years, or I guess 17. I guess I should have looked at my own figure. 17 years, right? Try to do math on the fly. So 17 years before we get the first one, right? First, decadal level flood. The next one happens pretty close to a decade. Next one happens in about 11 years. The next one happens within 5 years, right? So this notion, so you guys got it exactly. The system is the system. Nature is noisy. And even though we can calculate an average, and we have a large data set, and we look for the patterns over time over that whole area, that average is real. It's not a fake number, but it's not going to be perceived exactly evenly throughout that system. In some years, the decadal flooding is going to happen every 4 years. In some years, it's going to be happening every 28 years. And so if you're not clearly communicating that, someone might experience a flood, let's say in this event, and then think, oh, I have 10 years to rebuild, right? And oh my gosh, no, they're whacked in a couple of years. And they're like, what? These scientists don't know what they're talking about. They're just a bunch of idiots, right? That kind of stuff. Or similarly, and this is probably more problematic actually, which is this one here. So okay, we have a decadal flood here this year. Okay, cool. And then 10 years go by, no flood. 15 years go by, no flood. 20 years goes by, no flood. And it takes almost 30 years, right? So everybody here is forgotten, right? They grew up, they lived in this house for 15 years and never had to deal with the flooding, or their farm never had to deal with the flooding. And so we get lulled into this sense of safety that doesn't really exist. Okay, so that's a problem. The next thing is that, as I mentioned, to calculate robustly a 100-year flood frequency, we need a lot of data, and our stream gauge data are very sparse over the whole continent. So this is again a figure from the USGS, and let's check it out. So this is how many years of data we have been logging the water level in this drainage or in this stream. Okay, and this is the number of gauges that periodicity. So check it out. So here, this is 50 years right here, right? So the most common streams are have been collecting data for less than 25 years, right? And do we have some streams that we've been measuring for 100 years? Absolutely. The Mississippi and things of that nature, absolutely. But it's on the order of about 100-ish, right? In this whole continent. Or actually, well, it's more than the continent because it includes Hawaii and others too. But you know, that's crazy. So and it's not crazy. And I'm not faulting the USGS here. I'm just saying we don't have a massive long-term data set. But we're trying to estimate things like how frequently this event will occur over the course of a century. So we're using short-term data to estimate long-term. There's nothing wrong with that, but we have to realize that when we do that, we're going to have a much larger error rate. We're much more likely to get the specific number incorrect. And what does that look like in the real world? Well, this is Houston, just about the time of Hurricane Harvey, which struck a few years ago, and was one of the wettest rainfall events ever recorded in the U.S. And so this is the Harris County where the city of Houston lies, very flat, and each of these little dots is a stream gauge, okay, and the color represents how long we've been accumulating flows from that particular gauge. And so the darker the color, the longer the period. And so, yes, we do have a few of these that are on the order of 60-ish years, right, which is great. A few that are even older than that, which is great. But the vast majority of colors, as you look across this tapestry, are in the 10, 20-year range. Right? So we don't have a lot of good data. And then, as a consequence, which we haven't talked about yet, and we're probably going to run out of time today before we get to it too much, but suffice to say, the Federal Emergency Management Agency is one of the main entities that helps us try to deal with flood risk and things of that nature. They're dealing with it because they're trying to figure out how they might have to respond to flooding. And so they have these so-called floodplains that are 100-year and 500-year floodplains, meaning areas that are likely to flood, once in 100 years or once in 500 years. If you look at, that's not technically what they mean exactly, but that's what the implication is, right? So if I said a floodplain that's going to flood once in 100 years, like, that's cool. I should probably put my house there because it's not going to happen. It's not all that likely, right? Or 500 years. And so note that a lot of these areas, like this chunk here, this part of this floodplain, there's no stream gauges on, or there's very few stream gauges on it, right? So this lack of data is absolutely fundamentally important to understanding the problems with the notion of using a 100-year flood as a guiding, something to be guided by. So our data is not necessarily super long, and it's not spatially intense necessarily where we perhaps most need it. Okay, so we said floods are irregular. We said that our data is young and or sparse. And then the next part of this that's problematic is that these landscapes are not static. This is one of the most important points. So this is what I mean by that. So here's another example from the USGS. And here we're looking at, again, so here's a stream flow, cubic feet per second. Here's going back in time from the World War II, basically, to early 2000s. And here's this particular area in Illinois. And check it out. So here, before 1963, this is what the typical flooding was like, right? So we had some low flows, had some high flows, but it was pretty much, in this range. Yeah. Then we started putting in structures, impervious surfaces, concrete, all that kind of stuff. And as a consequence, now when it rains here, when it rains, a lot of that rain would, trickle down to the soil. and wouldn't make it into the channel per se. Not anymore. Now we have changed the landscape and we've made it more floody, more likely to flood, more flood prone. So now we're much more likely to see a really intensive flood, right? So the 100-year flood event back then was a bit less than 600 CFS. Now, now that's like a walk in the park. Look, almost every single year we get that level, right? So it used to be a once in a century thing is now like almost a once every year thing. And now the rare event would be something that's almost twice the discharge of those. Okay. Along with the fact that the landscapes aren't static, our climate is not static, as you guys all know. And so, so our climate is changing. And so again, if we're using, and maybe we're lucky, maybe we have some awesome data from our river, and we do have a stream gauge that's been there for 80 years, right? So we have a nice long data set. But the data that it's going to generate, let's say this is, the conditions 50 years ago, 60 years ago, right? And as the climate is rapidly changing, is that really relevant to our current rainfall patterns, our current situation? And this is a paper by Vogel that came out in about a decade ago, got a lot of attention. So they went and looked at this exact question. So they re-examined a lot of our long-term data sets that we were using to estimate flood risk and rates of flow, et cetera. And what they found is that floods are increasing or more likely to happen on the order of 2 to 3 times a decade. So the increase is that. So that as we go from the World War II to now, things are everywhere is on average more likely to be flowing faster and more intense. So even doing nothing else, doing no straightening of the rivers, doing no more urbanization, just the rainfall patterns themselves, the hydrology itself is getting more floody, okay? So when we have these estimates that were made off of old data that were probably generated a decade or 2 ago, those don't necessarily accurately reflect the risk that you and I are perceiving today. Okay, and then another one, this is sort of a nerdy kind of point that might be lost on some people, but it's very clear when you talk to mayors and the people that are actually dealing with floods and elected representatives that don't typically deal with hydrology, okay, not scientists, not flood experts or hydrologists, those types of folks. They oftentimes confuse what we're talking about. So this is what I mean by that. So when we talk about the peak of the water or the peak of the flows or the peak of the whatever, that's an estimate, right? And so in this case, this is the annual exceedance probability, or when are we going to get past a problem level, right? And this is how much flows are going on. This is a logarithmic scale again. We typically report out something like this solid line, right? The best fit of our models. But as with everything that we do, we're estimating, right? So there's really some error around it. And so so this is a common problem with all of our scientific outputs and technical outputs. But it's important here because people say, oh, it's the flood stage is whatever 12 feet, or this model is predicting the river is going to get to 12 feet above flood stage. Well, that's what the model predicts, but there's some error around there. It could easily get to 13 feet or something of that nature, right? And if the responders are planning, 12 feet, okay, this house will be safe or whatever. No, right? So so again, misinterpreting what the science is saying. And then lastly, which is probably the most important one, which is what you guys identified initially, right, with the problem with this 100-year flood situation, is that the very notion, how we verbally describe it, how we interpret it, leads us to problems because most of us don't understand probabilities and risk. And so this is what I mean. So when we say 100-year flood, what that actually means is a 1% chance of that level of flooding happening in a given year. And so we could say 1% chance, but the unfortunate choice was made in 1973 to, instead of saying a 100% chance, say 1 out of 100, and then we'll convert that to years. Okay, so 1 out of 100. So it sounds like, to me, it doesn't sound like it sounds rare, but what does that mean? If we have a 1% chance, that's a 1% chance every single year, right? So when we go through the math and do it, right, what that turns out is that, so I don't know how many of you guys own a house, probably not many of you guys own a house, but I am, right? So when I moved down here, we bought this house, and you typically get, so most people can't afford to just buy their house outright, especially in California, right? So what do? You go to the bank, get a loan, call it a mortgage, right? And so essentially what happens is the bank buys your house from the person, the seller, whatever, and then you spend the next several years paying back that loan to the bank with some interest, right? And we call that a mortgage. So people typically have a 15-year or a 30-year mortgage. They can refinance stuff, but typically most people have a 30-year mortgage. In other words, they're going to take 30 years and they're going to pay off every month or whatever. They're going to take 30 years to own their house. And at the end of that period, 30 years, then they will own outright the deed of their house. They're 100% the owner. They're good to go, right? So if most people are going to take 30 years to pay off their house, and we're talking about, and then their house is in, has a chance of flooding, a 1% chance of flooding in any one year, so therefore is in a 100-year flood plain, that means there's a 26% chance of their house flooding before they can pay off their house, right? Before they realize the maximum value of that house, and then could then, for example, in turn sell it and get 100% of the profit themselves. So that's a 1 in 3 chance. That's not very good, I would argue. So rather than talking about a 100-year flood, how about a 1 in 3 chance your house is going to flood before you pay it off? That's very different, right? It's the same math, the same underlying numbers, but I think that much more accurately conveys the risk. And for reasons that I will never understand, I think it's because we just thought everybody was stupid. I should be careful of that. Don't do judgment. Don't make judgment calls here in this class. So it's unfortunate that we did that. Other areas of the world have not taken that approach to risk and what is considered an acceptable risk. And the start of the conversation is not a 1 in 100-year chance or a 1% chance of happening in any one year, much, much higher. So the classic here, when we talk about flooding, the classic experts, we go over to Northern Europe and we go to the Netherlands, a country that's very low lying, where a large chunk of the country is actually at or below sea level. So they're very sensitive to flooding. These are the folks that, invented the windmill and all that kind of stuff to pump water. In the Netherlands, there's 1 or 2 exceptions, but by and large, when they talk about planning for cities, planning for freeways and infrastructure and stuff, their starting point is a 1 in 12,050 year acceptable rate. And then if something is important, is really valuable, hospital, power plant, they'll go to a 1 in 10,000 year probability, right? And so again, all they're doing there is instead of taking 1%, they're shoving it down to 0.1% or less, because they're saying, hey, the risk of this thing happening is too big for us. We don't want to gamble that way. So we want to make sure that we're going to design our, you name it, roadway, railway, apartment complex, whatever, such that it's very unlikely to happen. And that's what those folks use in other parts of the world. So in summary, Our 100-year flood fallacy is a huge problematic, and then we're almost ready for our break, is a huge problem. And this is, again, in my opinion, this is the biggest problem with dealing with flood risk in terms of disasters. We do not communicate properly at the level of risk that most of us are exposed to, either in our private property or in our public infrastructure. The key aspects of this are that floods are irregular, but we tend to talk about them as this sort of averaging number. The data that we use to parameterize these estimates of risk are imperfect. They're imperfect because the screen gauges are not numerically abundant, and or we've not been getting data long enough. 2, the landscapes are changing. We humans are modifying the landscape. So the flood, the ability of the system to flood is changing. On top of that, climate change is happening. So we're entering periods of where we're likely to see more intense flooding and more likely flood conditions or flood favoring conditions. We sometimes confuse when someone says a 12-foot high a flood, we sometimes think that means exactly 12 feet, when in reality there's a little bit of error and play around that, and that can be significant. And then lastly, all of this comes together to translate into a poor understanding of risk and complacency, because we think that we're safe, and complacency because we think that this seems like an acceptable level of behavior because of the way the risk has historically been presented to us for the last 50 years. Okay? Does that make sense, you guys?
Yeah.
Yes.
Questions about any of that? Okay. Why don't we're a little bit over, so why don't we take our 10-minute break right now, and we'll come back in 10 minutes and pick it up from here.